All right, so this is a video on LOL bar charts, which are a type of tool that we're going to use when we're solving problems where energy conservation comes into play. When will you want to use energy conservation is when sometimes the things that are happening in between two scenarios are too difficult to figure out what's happening, but energy can be a really powerful tool because it's path independent, which means it doesn't matter what's happening in between the two parts. Just like we saw in the steep slope lab. It doesn't matter how we got there, we get the same results. LOL bar charts are similar to the energy pie charts that we made, but they're quantitative. So we're going to be showing amounts of energy transferred around, and we're also going to have the system represented there so we can see energy getting transferred into and out of the system. It's going to allow us to track how energy is stored, transferred, and conserved. So we can show it entering and leaving a system, and we can also see what types of energy that we have present. Some problem-solving strategy. I would say the most important thing to do is decide what energy types are present in the before and after scenarios. So we learned about several types of energy before. We learned about kinetic energy or energy of motion. We learned about gravitational potential energy, which is stored in a field between an object and another object through the force of gravity. We learned about elastic potential energy, which is energy stored in a stretched or compressed thing, such as a spring or a rubber ball. We learned about thermal energy, which is heat, sometimes known as the change in internal energy. And then we also talked about how in the pie charts, we showed how you might be able to represent the different amounts of these. With these, with the LOL charts, the most important thing is, or another important thing is defining the system and saying, is energy going into or out of the system? So we're going to be using the principle of conservation of energy, which is the idea that energy cannot, at least in our common physics 1 scenarios, we're not going to have energy created or destroyed. However, it might change forms into something that's not considered very usable, like heat, and it also might get transferred outside of the system through interactions. So anytime you have something like a collision or friction between two objects and one object isn't in the system, then we can transfer energy out of that. All right, so we're going to go through 3 examples. The first 2 examples are identical, but they have different ways of defining the system, and then the third one is different. So in our first example, we have a softball at rest in the hand of a softball player, and then afterwards, we have the softball in motion at the highest point in its trajectory. So that's at the bottom and at the top. We obviously have change in types of energy here, and our system is going to be the player, ball, and earth. So let's go through how this LOL chart is set up. On the left, we have the before. On the right, we have the after, and the middle of this O shape is actually just for defining our system. You'll see why in a second. So here's our system, the player, ball, and earth. We were given that, but sometimes you might have to decide what the system is. Because the ball is a little bit above the ground to begin with, we're going to give it a little bit of gravitational potential energy. Afterwards, the ball is at a higher point, so it's actually got more gravitational potential energy. It has the potential to fall down further. It's also still moving, so because it's a projectile and not just thrown straight up, it's still moving even when it's at the highest point. So we have our kinetic energy as well. Now, the last question is, where did the energy come from? So this player did some work on the ball, so she used a force to move it. But we don't actually need to show that work in here. We're just saying that what allowed her to throw the ball to begin with is that she had some energy in her body, which she used for doing this exercise. So it used to be stored in her muscles as glycogen or whatever. And then we have that's chemical energy that she's converting into motion. So this is a way to do it when we have the player as part of the system. There's a second way of doing this, which is defining the system as just the ball and earth. So when we start combining conservation of energy and conservation of momentum, you're going to realize that sometimes it's easier to have something part of your system, and sometimes you're going to have it's going to be easier for it to be defined as outside of your system. So let's look at what this looks like if our system is just the ball and the earth. So exact same scenario, the softball's at rest and then it's in motion. Our system now does not include the player, it's just the ball and the earth. We still have gravitational energy before that's stored in the field between the softball and the earth. That's why the earth is part of the system, by the way. One other important thing to note is that when you see the earth as part of a system, it's there so that you can define the gravitational energy, because gravitational energy is not in an object and it's not in the earth, it's in the field between them. It's generally separate from the ground or any other surface that things might be moving on. So if you want that surface to be in there, you have to put it in there as the surface, like the road or the track or whatever things are moving on. And then we have a little bit more gravitational potential energy at the end. It also has some kinetic energy at the end. So now we have 1 bar of energy before, 3 bars of energy afterwards. So our question is, where did the energy come from? Following the law of conservation of energy, you can't create or destroy energy. So that means that we have to have energy coming into the system. In the previous slide, we said that since the player was part of the system, she originally had some chemical energy in her body that she converted into this motion. Now the player's outside of our system, so we're going to show that chemical energy from the player out of the system, and then we're going to show it getting transferred in. So this allows us to follow the law of conservation of energy, even though we have more bars afterwards than before. We're showing that the energy is coming from somewhere. All right, in our last example, I'm going to show you how we might include heat in here. So in this one, we're changing the scenario slightly. We're going to have the softball already in motion at the beginning. And at the end, the softball is going to be at rest in the catcher's mitt. So basically, one player's throwing it, it's going through the air. We're not going to examine what's happening in the air because this is, as I said before, energy is path independent. So what that means is we're only looking at the before and after, not in the middle in this case. And then we might be able to wonder at the end, where did the energy go? So our system here is going to be just the ball and the earth. So that means that neither player and not the catcher's mitt is going to be included in this. All right, in the beginning, we have some kinetic energy because the ball is in motion already. And we also have a little bit of gravitational energy. Now, because this is at the same height afterwards, we're going to give it the same amount of gravitational energy. So you might also be wondering, how do I know if there's gravitational energy there or not? If you have something happening on a perfectly flat surface, so for example, a hockey puck sliding across ice at constant speed, you don't need to include any gravitational energy because it's happening at the same height the whole time. Gravitational energy is defined by changes, so I could just have easily made this pie chart with no gravitational energy in it. Because it's happening a little bit above the ground, I wanted to give I wanted to make it possible for this to go up and down by giving them an initial bar of gravitational energy. If I had the ball end lower, then I would definitely want to give it some gravitational energy to start with. In this case, it's at the same height, so it should have the same amount of gravitational energy before and after. All right, after the collision, you might be wondering what happened to, so the ball goes into the catcher's mitt, what happened to it, right? It's where did the kinetic energy go? So we learned in class that collisions generate heat. And I showed that with 2 metal balls. If you weren't here, ask for a demo of this, but I have these 2 metal balls, and when you click them together with a piece of paper in between them, it actually generates so much heat that it burns a hole in the paper. And you can smell the singe of that. Anytime you have 2 objects colliding, you're going to have a little bit of heat unless it's called later we'll learn the term perfectly elastic collision. So that one generates no heat, but in the real world, they almost all generate heat. So anyway, when the ball hits the mitt, there's going to be some heat generated. So we're going to put a little bit of heat in the softball. However, some of that heat is also going to go into the catcher's mitt. So and since the catcher's mitt is not part of the system, we need to show that as heat coming from outside the system. So or rather heat going to outside the system. So at the end, this is going to be one where some of the energy leaves the system instead of some of the energy coming into the system. All right, so I hope you've enjoyed this video on LOL charts. A couple warnings for the problems that you're about to do. Just make sure that you know exactly what's in your system. If you have things like friction or collisions with objects from outside the system, then you are going to definitely transfer energy out. So look for that kind of scenario. If you have things happening on a flat surface, you don't need to include gravitational energy in there. And then if you're wondering where did the energy go at the end, chances are it's in the form of heat. That's it. So I hope you enjoyed this video. I hope it was informative.